When the Industrial Revolution started, the amount of carbon sitting underneath Britain in the form of coal was as big as the amount of carbon sitting under Saudi Arabia in the form of oil. And this carbon powered the Industrial Revolution. It put the great in Great Britain and led to Britain's temporary world domination. And then in 1918, coal production in Britain peaked and has declined ever since. In due course, Britain started using oil and gas from the North Sea, and in the year 2000, oil and gas production from the North Sea also peaked, and they're now on the decline. These observations about the finiteness of easily accessible, local, secure fossil fuels, this is a motivation for saying, well, what's next? What is life after fossil fuels going to be like? Shouldn't we be thinking hard about how to get off fossil fuels? Another motivation, of course, is climate change. And when people talk about life after fossil fuels and climate change action, I think there's a lot of fluff, a lot of greenwash, a lot of misleading advertising. And I feel a duty as a physicist to try to guide people around the claptrap and help people understand the actions that really make a difference and to focus on ideas that do add up. Let me illustrate this with what physicists call a back-of-envelope calculation. We love back-of-envelope calculations. You ask a question, you write down some numbers, and you get yourself an answer. It may not be very accurate, but it may make you say, So here's a question. Imagine if we said, oh yes, we can get off fossil fuels, we'll use biofuels. Problem solved. Transport, we don't need oil anymore. Well, what if we grew the biofuels for a road on the grass verge at the edge of the road? How wide would the verge have to be for that to work out? Okay, so let's put in some numbers. Let's have our cars go at 60 miles per hour. Let's say they do 30 miles per gallon. That's the European average for new cars. Let's say the productivity of biofuel plantations is 1,200 litres of biofuel per hectare per year. That's true of European biofuels. And let's imagine the cars are spaced 80 metres apart from each other, and they're just perpetually going along this road. The length of the road doesn't matter, because the longer the road, the more biofuel plantation we've got. What do we do with these numbers? Well, you take the first number and you divide by the other three, and you get 8 kilometres. And that's the answer. That's how wide the plantation would have to be, given these assumptions. And maybe that makes you say, maybe this isn't going to be quite so easy. And it might make you think, perhaps there's an issue to do with areas. And in this talk, I'd like to talk about land areas and ask, is there an issue about areas? The answer is going to be yes, but it depends which country you are in. So let's start in the United Kingdom, since that's where we are today. The energy consumption of the United Kingdom, the total energy consumption, not just transport, but everything, I like to quantify it in light bulbs. It's as if we've all got 125 light bulbs on all the time. 125 kilowatt hours per day per person is the energy consumption of the UK. So there's 40 light bulbs worth for transport, 40 light bulbs worth for heating, and 40 light bulbs worth for making electricity, and other things are relatively small compared to those three big fish. It's actually a bigger footprint if we take into account the embodied energy and the stuff we import into our country as well. And 90% of this energy today still comes from fossil fuels, and 10% only from other greener, possibly greener sources like nuclear power and renewables. So, that's the UK, and the population density of the UK is 250 people per square kilometre. And I'm now going to show you other countries by these same two measures. On the vertical axis, I'm going to show you how much light bulbs, what our energy consumption per person is. And we're at 125 light bulbs per person, and that little blue dot there is showing you the land area of the United Kingdom. And the population density is on the horizontal axis, and we're at 250 people per square kilometre. Let's add European countries in blue, and you can see there's quite a variety. I should emphasise both of these axes are logarithmic. As you go from one grey bar to the next grey bar, you're going up a factor of 10. Next, let's add Asia in red, Middle East and North Africa in green, Sub-Saharan Africa in blue, black is South America, purple is Central America, and then in pukey yellow we have North America, Australia and New Zealand. And you can see the great diversity of population densities and of per capita consumptions. Countries are different from each other. Top left, we have Canada and Australia with enormous land areas, very high per capita consumption, 200 or 300 light bulbs per person, and very low population densities. Top right, Bahrain has the same energy consumption per person roughly as Canada, over 300 light bulbs per person, but their population density is a factor of 300 times greater, 1,000 people per square kilometre. Bottom right, Bangladesh has the same population density as Bahrain, but consumes 100 times less per person. Bottom left, well, there's no one, but there used to be a whole load of people. Here's another message from this diagram. I've added on little blue tails behind Sudan, Libya, China, India, Bangladesh. That's 15 years of progress. Where were they 15 years ago and where are they now? And the message is most countries are going to the right and they're going up and to the right. Bigger population density and higher per capita consumption. So we may be off in the top right-hand corner, slightly unusual, the United Kingdom accompanied by Germany, Japan, South Korea, the Netherlands, and a bunch of other slightly odd countries. But many other countries are coming up and to the right to come and join us. So we're a picture, if you like, of what the future energy consumption might be looking like in other countries too. And I've also added in this diagram now some pink lines that go down and to the right. And those are lines of equal power consumption per unit area, which I measure in watts per square meter. So, for example, the middle line there, 0.1 watts per square meter, is the energy consumption per unit area of Saudi Arabia, Norway, Mexico in purple, and Bangladesh 15 years ago. And half of the world's population lives in countries that are already above that line. The United Kingdom is consuming 1.25 watts per square meter. So is Germany, and Japan is consuming a bit more. So, let's now say why this is relevant. Why is it relevant? Well, we can measure renewables in the same units and other forms of power production in the same units. And renewables is one of the leading ideas for how we could get off our 90% fossil fuel habit. So here comes some renewables. Energy crops deliver half a watt per square meter in European climates. What does that mean? And you might have anticipated that result given what I told you about the biofuel plantation a moment ago. Well, we consume 1.25 watts per square meter. What this means is even if you covered the whole of the United Kingdom with energy crops, you couldn't match today's energy consumption. Wind power produces a bit more, 2.5 watts per square meter, but that's only twice as big as 1.25 watts per square meter. So that means if you wanted literally to produce our total energy consumption in all forms, on average from wind farms, you'd need wind farms half the area of the UK. I've got data to back up all these assertions, by the way. Next, let's look at solar power. Solar panels, when you put them on a roof, deliver about 20 watts per square meter in England. If you really want to get a lot from solar panels, you need to adopt the traditional Bavarian farming method, where you leap off the roof and coat the countryside with solar panels too. Solar parks, because of the gaps between the panels, deliver less. They deliver about 5 watts per square meter of land area. And here's a solar park in Vermont with real data delivering 4.2 watts per square meter. Remember where we are, 1.25 watts per square meter, wind farms 2.5, solar parks about 5. So whichever of those renewables you pick, the message is, whatever mix of those renewables you're using, if you want to power the UK on them, you're going to need to cover something like 20% or 25% of the country with those renewables. And I'm not saying that's a bad idea, we just need to understand the numbers. I'm absolutely not anti-renewables. I love renewables, but I'm also pro-arithmetic. Concentrating solar power in deserts delivers larger powers per unit area because you don't have the problem of clouds. And so this facility delivers 14 watts per square meter, this one 10 watts per square meter, and this one in Spain 5 watts per square meter. Being generous to concentrating solar power, I think it's perfectly credible it could deliver 20 watts per square meter. So that's nice. Of course, Britain doesn't have any deserts. Yet. So here's a summary so far. All renewables, much as I love them, are diffuse. They all have a small power per unit area, and we have to live with that fact. And That means if you do want renewables to make a substantial difference for a country like the United Kingdom, on the scale of today's consumption, you need to be imagining renewable facilities that are country-sized. Not the entire country, but a fraction of the country, so a substantial fraction. There are other options for generating power as well, which don't involve fossil fuels. So there's nuclear power, and on this Ordnance Survey map, you can see there's a size well B inside a blue square kilometre. That's 1 gigawatt in a square kilometre, which works out to 1,000 watts per square metre. So by this particular metric, nuclear power isn't as intrusive as renewables. Of course, other metrics matter too, and nuclear power has all sorts of popularity problems. But the same goes for renewables as well. Here's a photograph of a consultation exercise in full swing in the little town of Pennycook, just outside Edinburgh, and you can see the children of Pennycook celebrating the burning of the effigy of the windmill. So people are anti-everything, and we've got to keep all the options on the table. What can a country like the UK do on the supply side? Well, the options are, I'd say, these three. Our renewables, and recognizing that they need to be close to country-sized. Other people's renewables, so we could go back and talk very politely to the people in the top left-hand side of the diagram and say, we don't want renewables in our backyard, but please could we put them in yours instead? And that's a serious option. It's a way for the world to handle this issue. So countries like Australia, Russia, Libya, Kazakhstan could be our best friends for renewable production. And a third option is nuclear power. So that's some supply-side options. In addition to the supply levers that we can push, and remember, we need large amounts because at the moment we get 90% of our energy from fossil fuels. In addition to those levers, we could talk about other ways of solving this issue. Namely, we could reduce demand, and that means reducing population, I'm not sure how to do that, or reducing per capita consumption. So let's talk about three more big levers that could really help on the consumption side. First, transport. Here are the physics principles that tell you how to reduce the energy consumption of transport. And people often say, oh yes, technology can answer everything. We can make vehicles that are 100 times more efficient. And that's almost true. Let me show you. The energy consumption of this typical tank here is 80 kilowatt hours per 100 person kilometers. That's the average European car. 80 kilowatt hours. Can we make something 100 times better by applying those physics principles I just listed? Yes, here it is. It's the bicycle. It's 80 times better in energy consumption, and it's powered by biofuel, by Weetabix. And there are other options in between, because maybe the lady in the tank would say, no, 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 that's a lifestyle change. Don't change my lifestyle, please. So, well, we could persuade her to get into a train, and that's still a lot more efficient than a car, but that might be a lifestyle change. Or there's the eco-car, top left. It comfortably accommodates one teenager, and it's shorter than a traffic cone, and it's almost as efficient as a bicycle, as long as you drive it at 15 miles per hour. In between, perhaps some more realistic options on this lever, the transport lever, are electric vehicles, so electric bikes and electric cars in the middle, perhaps 4 times as energy efficient as the standard petrol-powered tank. Next, there's the heating lever. Heating is 1/3 of our energy consumption in Britain, and quite a lot of that is going into homes and other buildings doing space heating and water heating. So here's a typical crappy British house. It's my house with the Ferrari out front. What can we do to it? Well, the laws of physics are written up there, which describe how the power consumption for heating is driven by the things you can control. The things you can control are the temperature difference between the inside and the outside. And there's this remarkable technology called a thermostat. You grasp it, you rotate it to the left, and your energy consumption in the home will decrease. I've tried it. It works. Some people call it a lifestyle change. You can also get the fluff men in to reduce the leakiness of your building. Put fluff in the walls, fluff in the roof, and a new front door, and so forth. And the sad truth is, this will save you money. That's not sad, that's good. But the sad truth is, it'll only get about 25% off the leakiness of your building if you do these things, which are good ideas. If you really want to get a bit closer to Swedish building standards with a crappy house like this, you need to be putting external insulation on the building, as shown by this block of flats in London. You can also deliver heat more efficiently using heat pumps, which use a smaller bit of high-grade energy like electricity to move heat from your garden into your house. The third demand-side option I want to talk about, the third way to reduce energy consumption, is read your meters. People talk a lot about smart meters, but you can do it yourself. Use your own eyes and be smart, read your meter, and if you're anything like me, it'll change your life. Here's a graph I made. I was writing a book about sustainable energy, and a friend asked me, well, how much energy do you use at home? And I was embarrassed, I didn't actually know. And so I started reading the meter every week, and the old meter readings are shown in the top half of the graph, and then 2007 is shown in green at the bottom, and that was when I was reading the meter every week, and my life changed because I'd started doing experiments and seeing what made a difference, and my gas consumption plummeted because I started tinkering with the thermostat and the timing on the heating system, and I knocked more than a half off my gas bills. There's a similar story for my electricity consumption, where switching off the DVD players, the stereos, the computer peripherals that were on all the time, and just switching them on when I needed them, knocked another third off my electricity bills too. So we need a plan that adds up. And I've described for you 6 big levers. And we need big action because we get 90% of our energy from fossil fuels. And so you need to push hard on most, if not all, of these levers. And most of these levers have popularity problems. And if there is a lever you don't like the use of, well, please do bear in mind that means you need even stronger effort on the other levers. So I'm a strong advocate of having grown-up conversations that are based on numbers and facts. And I want to close with this map that just visualizes for you the requirement of land and so forth in order to get just 16 light bulbs per person from 4 of the big possible sources. So if you wanted to get 16 light bulbs, remember today our total energy consumption is 125 light bulbs worth. If you wanted 16 from wind, this map visualizes a solution for the UK. It's got 160 wind farms, each 100 square kilometers in size, and that would be a 20-fold increase over today's amount of wind. Nuclear power, to get 16 light bulbs per person, you'd need 2 gigawatts at each of the purple dots on the map. That's a 4-fold increase over today's levels of nuclear power. Biomass, to get 16 light bulbs per person, you need a land area, something like 3.5 Waleses worth, either in our country or in someone else's country, possibly Ireland, possibly somewhere else. And the fourth supply-side option, concentrating solar power in other people's deserts. If you wanted to get 16 light bulbs worth, then we're talking about these 8 hexagons down at the bottom right. The total area of those hexagons is 2 greater Londons worth of someone else's Sahara. And you'll need power lines all the way across Spain and France to bring the power from the Sahara to Surrey. We need a plan that adds up. We need to stop shouting and start talking. And if we can have a grown-up conversation, make a plan that adds up, and get building, maybe this low-carbon revolution will actually be fun. Thank you very much for listening.